With Lambda calculus, we need a lot of context before we can finally do something. So my apologies that this first video comes so very, very late in the module. What we're doing now is evaluating the expression if true t f. T and f are just unbound variables. If and true are exactly as they're defined in the notes. You'll notice that I'm not using double square brackets here for if and true. I just don't have the graphics for that in this environment. But for these names we recognize, in this case just if and true, we will expand them how they are expanded in the notes. Now, if true tf is parenthesized this way because you do the applications left to right. So if applies to true, the result of that applies to t, and the result of that applies to f. This is also shown graphically here, where the if true application is contained inside of the application of that result to t, which is contained inside of the application of that result to f. We're using AOR here, so we're simply going to go left to right. That means the first thing we have to do is expand if. So coming down a step, here in the left part of this green box, we will expand the if to this. If is defined as lambda b dot lambda t dot lambda f dot btf. You'll note that we've actually named these b prime 1, t prime 2, f prime 3. This is just an alpha renaming. There can be problems if you just keep the variable names the same. You can confuse one variable with another. So every time we do an application, substitution, or expansion in this lambda calculus reducer, we'll give these prime names, like b prime 1, t prime 2, just so we don't get them mixed up. So now we have lambda b prime 1 dot lambda t prime 2 dot lambda f prime 3 dot btf, all applied to true. There's no further application we can do within this lambda, and we're going to do the innermost left to right, because this is AOR. So now we expand true. True is simply lambda x dot lambda y dot x, with some primes there to avoid name clashes. Now we've expanded the if, and we've expanded the true, so we can apply, and application is simply substituting the b, named by lambda b here, with the argument to this application, which is lambda x dot lambda y dot x. So we're going to keep this box, which is the pink box here, but wherever it lists b1, which is here, we're going to substitute in the argument to this application, which is lambda x, lambda y, x. So this gets substituted in right here, which was right here in the original expression. And now we're left with lambda t dot lambda f dot x dot y dot x tf tf. This is t and f as variables. These are our free variables. Really, we just want t to come out on top because this was if true tf, where t is the if branch. You can see the parenthesization here. In this case, it's not that important. We're mostly just doing things left to right, but it is critical in certain cases to remember how these things are parenthesized, and the fact that when you substitute out a variable, you may be substituting it for an entire expression. Now, as we go in, we look for applications we can do. We want the innermost, leftmost application. Lambda x dot lambda y dot x is applied to t, so we can do that application by substituting this t for this x in this expression. The only use of that x was x here, so the x6 is going to be replaced by t2. As we come down here, indeed, that's what happened. This whole application went away, and the x6 got replaced by t2. Now, in the lambda y, t, we replace y with f. Remember, this was an if true, so we should expect the false branch to go away. And indeed, it goes away precisely because y isn't used in this expression. If I substitute f in for y7, well, there are no y7s in the body of this lambda, so that substitution does nothing. And we just end up with t2, which was the body of this lambda in the first place, unchanged. Now we have lambda t2 dot lambda f3 dot t2 applied to t applied to f. And you'll note, even with all of those steps, this is just our definition of true. If true did a lot of work just to get true out the other side. We apply if true to t, so t2 in this body gets substituted for the free variable t. Now we have lambda f3 dot t, and again, since the whole purpose of true is to take its first argument, when we apply this result to f, that f is simply discarded. We can now lose the lambda entirely because we did the application, and our final result is simply t. So given our original expression, if true, tf, through all of these steps, we did eventually come down to true. Now for symmetry, let's briefly look at if false, tf. The substitution of if is exactly the same. False is lambda x dot lambda y dot y. When we substitute that through, we end up with lambda x dot lambda y dot y applied to tf. The whole point of true and false is that true reduces to its first argument, while false reduces to its second, and indeed, y is all we get out of this. So after a couple steps, we end up with lambda t dot lambda f dot f. Again, if is a complicated way just to get back to the Boolean itself. Now we have false applied to t applied to f. True evaluates to its first argument, false evaluates to its second. So with the first argument, false is simply going to discard it. The free variable t is now gone. Now we have lambda f dot f applied to f. The free variable f substitutes in, and indeed when we said if false tf, we get f. Of course, it's all rather pointless to simply have if true or if false, but as we get slightly further into the module, you'll see more interesting data structures and the ability to check things about them that will evaluate to true or false. Usually this false would be a more interesting expression.